Next up is Chris Anderson. Chris is the former editor-in-chief of Wired magazine and the CEO of 3DR. I am a fan of his work with the DIY community through the DIYDrones and DIYRobocars initiatives, and looking forward to hear about racing robocars and how we can all use AI on Edge's devices. Welcome, Chris.
Hi, I'm Chris Anderson, CEO of 3DR and one of the founders of the DIYRobocars Racing League. And today I'm going to talk to you about how we use small-scale racing cars to teach and explore deep learning AI and some of the new techniques you've been hearing about elsewhere at this conference. So we call these robocars, and the way we should think about small scale is this famous quote from Chris Dixon that from Andreessen Horowitz, the VC firm, that the next big thing will start out looking like a toy. And you probably think of things like GPUs, which started as for video games, and some of the early robots were toys as well. And this is something I've got a lot of experience in because we started that more than 10 years ago with drones. At the dawn of the sort of smartphone era, the year that the iPhone came out, 2007, there were a bunch of other things that came out that year. There was Arduino, there was the maker movement, there was 3D printing. And I at the time still have 5 children and was trying to get them interested in technology. And so I thought to myself, well, robots. And they said, well, we got Lego Mindstorms and it wasn't as exciting as they'd hoped. And so I said, well, what about flying robots? And they said, well, what does that mean? And I wasn't quite sure. So Googled flying robots, turns out it's a drone. Googled drone, what's a drone? Turns out it's a plane with a brain. What kind of brain? Autopilot. How does it work? Turns out it's many of the same components that's in a smartphone. Sensors, GPS, wireless, cameras, things like that. So we just decided to do it and did it on the dining room table first with Lego and then started a community called DIYDrones, do-it-yourself drones, which at the time seemed crazy. Drones were military industrial, they were weapons, they were aerospace, they cost hundreds of millions of dollars and you couldn't have one. Now how could you DIY? And the answer is you just use these same parts that are in your phone and you just assemble them differently. And here you can see the picture of our first production line. Where our children, or some of our children, are assembling kits with literally Lego parts to sell at a maker fair. It was a robotic blimp. And this seemed silly. It seemed like a toy, but the community grew very quickly, became one of the largest robotics communities in the world. And literally 5 years later, by 2012, this was one of the largest drone production facilities in North America, continuously coming out of this open source, people just hacking together bits and pieces, and it just got better and better and better. And today the drones that you can buy in any store and that you're familiar with all emerged out of this DIY movement. So the future of aerospace turned out to be bottoms up, turned out to be sort of open source, turns out to look more like Silicon Valley than it did like the traditional aerospace industry. And that was inspiring, but that was 10 years ago. Now we fast forward and, the drones are done, they work, but cars, autonomous cars, self-driving cars are not done. You don't have one, probably. I don't have one, at least not a full-size one. And it's they're not ubiquitous. And even if you did have access to one, it's probably because you work for Google or Uber or Tesla, and and they're not maybe fully self-driving yet, and they're certainly not racing. So we thought, well, let's do the same thing. Let's put the letters DIY in front of robocars and see what we could do by, once again, using these easy, accessible technologies to explore cutting-edge technical problems. So this is the way we started, in a big warehouse with lines painted on the ground, and the jankiest things you could imagine. But over time, it got better, as you might imagine. And I have Adam Conaway from Databricks was one of the founders, and he came up with a project they called Donkey Car, and him and his co-founder there have one of the early donkey cars. And Donkey Car was the notion of using a Raspberry Pi and a deep learning framework. In this case, you would gather data by driving it manually around a track, And then you have a pair of images and inputs. And then you would upload that pair of the two data sets to the cloud, where it would train a deep learning algorithm, a deep learning model, and then you would download that model and then run it in real time so the car could drive autonomously. This is called behavioral cloning. You're basically copying a human driver. And so, it evolved a little bit. And today, Donkey Car looks like this, and it's a very popular framework that is pretty easy. It's just an RC car. It's a 3D printed shell. It's a Raspberry Pi or a Jetson Nano, and a camera. And it's super simple, and yet it's very effective, and it goes quickly, as I'll show you in a moment. And so the enabling technologies here were like TensorFlow. The fact that we have a deep learning framework that's easy to use and runs well in the cloud. Then we have Python, of course, which we use as our kind of overall glue framework. And then you have very cheap, powerful single board computers like Raspberry Pi and Jetson Nano, and now there's others coming out from Google with the Coral framework and others. So this is really why it's possible to now do DIY racing cars in the way we did DIYDrones. Rather than the iPhone, which we had in 2007, we have this category of AI technologies, including the cloud, that allows us to do the same thing now. And so we said, well, okay, we're doing it in small scale, but remember this could scale up. And this is one of our easy, earlier experiments, putting it on a go-kart. What's funny about this particular example is that the guy, the crash test dummy in the go-kart is Carl Bass, who at the time was the CEO of Autodesk. He and his son had designed this go-kart, and then he allowed us to sort of take away the human driving elements and basically replace him with a computer vision, deep learning, self-driving framework. And all he had was that red button on the steering wheel. All he could do was kill it. The rest of it, he was just a passenger as it drove around. Now, fortunately, we nobody got hurt, and it all worked fine. But this is just an example of how we can sort of DIY right up into things that could carry a person. This here is an example of Donkey Car running now at the AWS, the Amazon AWS conference. And as you can see, it goes perfectly fine. It's trained to do this on its own, and that's about, I would call, half speed. We now go much faster, but what's interesting about that is that it could go anywhere. It's been trained to look at lines, look at whites and yellows and things like that, look at cones, and just extend that to real world examples. And we're going much further than that now to introduce other technologies beyond even cameras to go further. This is an example of another kind of approach. In this approach, this one looks up and is looking at cones, and it's looking both up at the lights and down at the cones. And what it does is it localizes itself on the track based on where it observes these cones, and then creates a particle filter and sort of estimates its position. So that's another really cool technique that actually just used traditional computer vision. No deep learning in this one at all, but it's very effective on this course where you do have cones. And you can see it's doing about 10 miles an hour in real time. But remember, this is like a 1/10 scale car, so it's like 100 miles an hour in scale speed. Another example here is just sort of showing how we map what we're doing to what the full scale autonomous cars are doing. So just to give you an example of our car's sort of technology suite versus a Google Waymo technology suite. And as you can see, Google Waymo car, which probably costs $1 million, has more of everything. It has more. We'll use 1 or 2 cameras. They'll use 5 or more. We use something like a Raspberry Pi or a Jetson Nano, and they'll use lots of NVIDIA TX2s and Xaviers and beyond. We might use radar, probably not. They use lots of radar. We use 2D LiDARs that cost $60. They'll use 3D LiDARs that cost $70,000 or more. You can't even buy them. They're custom LiDARs. We can use GPS outside. They use GPS. Maybe theirs is better. We use wheel encoders. They use wheel encoders. We have IMUs on board. which we can use for inertial sensing, so do they. We use things like TensorFlow, OpenCV, PyTorch, things like that. They use the same frameworks, but they're doing more custom code. Our simulator is based on Unity. Their simulator is based on Unity, and ours costs $200 or $300, and theirs is like $1 million. So it's relevant. What we're doing here seems like a toy, but it's extremely relevant to what's going on in the real world, and it's more than just a sort of a faded approximation of what they're doing in the real world. By racing, by going head to head and going fast, we're actually doing something they're not doing. And when you think about it, the history of automotive innovation has always come through racing. Le Mans, Formula One, Indy 500, all the car companies develop and test their new engines, transmissions, bodies, everything on the racetrack, except for self-driving cars. Self-driving cars are all about safety, not performance. And yet when you think about it, performance can be a way to achieve safety. Right now, when a self-driving car isn't quite sure what to do or senses a collision, it'll just put on the brakes. And so as a result, they're extremely conservative drivers on the road. And right now, we're already seeing here in the Bay Area, where we have a lot of self-driving cars in R&D, that they're causing traffic jams. It's actually slowing down traffic because they're so conservative. But as you know, there's other ways to avoid an accident. One can just be nimble. You can very, very quickly steer away. And so, that's an approach that racing allows us to explore. Aggressive driving as a way to achieve safety, which is to say, avoid collisions, as opposed to very conservative driving. Plus, we're just exploring a dimension of self-driving cars that isn't being explored well anywhere else. I mentioned that we use simulators, and this is sort of an example of how we do it. This is really the golden age of simulation. We have not only amazing game engines with Unity and Unreal, we have the ability to run them in cloud. So we not only have GPUs, but we have cloud-based GPUs. We have the ability now to script these things with because they have fantastic physics engines, and they become photorealistic, and the so-called sin to real gap is shrinking very quickly. In addition, now that we're in COVID and quarantine, we've actually been doing a lot of our races in simulation. So it's really given us an opportunity to not only improve our simulation, but also include people who can't be with us in person. So we run these virtual races online, and people from around the world, Japan, we have a number of our team lead is from France, and we have throughout Asia and Latin America, we have participants. So that's fantastic. And then finally, the great thing about simulation is it allows us to move beyond behavioral cloning to reinforcement learning. And reinforcement learning, as you know, is one where you basically give the code, give your algorithm some goals. Stay on the track, avoid the cones, etc. So these are punishments and rewards. And then you run it thousands and thousands of times against the different scenarios. And then it creates the weights based on that, whichever combination of outputs led to the highest rewards and fewest punishments. That's something, that repetition, being able to create lots of different scenarios and run lots of different training runs is really difficult to do in the real world. And yet in simulation, we can synthetically create any number of scenarios and run massively parallel races to build these reinforcement learning networks, and then transfer them to the real world, where presumably they would do as well. And if they don't, we can do better. So this is an example of just the our simulator simulating a real world course rather, in Colorado that was called the Autonomous Vehicle Competition. It no longer exists in the real world, but it does now exist in simulation. So I want to talk a little bit about the different approaches we use. There's basically 4 different kinds of robocars that we work with in our community. There's traditional computer vision and OpenMV, which is a very inexpensive single board computer camera combination, costs about $60. That's sort of the easiest way. You script in MicroPython. It uses basically the OpenCV framework, and that's classic computer vision. A very good way to go fast, although sometimes can be inflexible. You have to tune it for whatever the lighting and shadows might be at the moment. There's a lot of custom ones that involve either computer vision code or deep learning code. Sometimes bring in LiDAR sensors, bring in multiple cameras, stereo vision, sometimes depth cameras, things like the Intel RealSense series. And the one I showed you before that was looking at cones is called Cone Slam. SLAM means simultaneous location and mapping. And so those are very interesting experiments in novel techniques. Then there's behavioral cloning, which is Donkey Car. We just talked about that. And then there's reinforcement learning, which is some of the other techniques from companies like Amazon that I'll talk about in a second. So those are the kind of different approaches, and there's not like one that's better than others. Any one of them could win. As it happens right now, computer vision, just because it seems to be tuned, and the custom tech cars, which are super tuned, seem to be going faster, but there's no reason why the others couldn't catch up. And for example, here's our track record. What you have here is the red is the computer vision approaches, the blue is the deep learning approaches. As you can see over time, there's sometimes one is faster than the other. What's interesting is that we've also timed the fastest human, or fastest human we know, on the course, and you can see that earlier this year the computer vision cars became faster than the fastest humans, and the deep learning cars are probably going to get there as well on any given race. It may be that the deep learning networks or models are not as well trained as they might be, or they haven't had as much training time as they want. But we expect that both computer vision and deep learning will surpass the fastest humans on any track that we know this year. And that's because they have such fast reaction times. They're thinking in terms of milliseconds, and humans who are forced to work, to make it apples to apples, we make the humans work with first-person view goggles. So they both have the same view from the car. The humans are looking through a camera. The AI is looking through a camera. When the camera's down that close to the ground, it's quite hard to figure out where you are. And so the humans really just cannot compete with deep learning in that scenario. There's been a lot of technologies. I think I mentioned some of them before, like TensorFlow, etc. But when you think about it, we're having a very similar moment to what we had with the iPhone. The iPhone introduced MEMS sensors and ARM core processors and GPS and batteries and wireless networks and all sorts of great technologies, where it's now suddenly super cheap because of the scale of smartphones. And now we're seeing these other enabling technologies doing the exact same thing for autonomous cars. We have really great depth sensing and motion capture technology with the Intel RealSense series. LiDAR, which used to cost $70,000 or more, 2D LiDAR is now under $100 at a 10-meter range, and as much as 10,000 points per second. The single board computers are fantastic. The Raspberry Pi 4 was 3 and 4 were our starters, but now the Jetson Nano, which is designed for deep learning, has now cost us $59, which is just kind of incredible. And then we have these integrated computer vision cameras, which is a camera plus a chip, which is running typically MicroPython and some sort of computer vision framework. These also cost about $60, and you can raise it. Basically, that's all you need to run a car. As a result, we now get all the stuff that the real world autonomous cars get. We can localize ourselves. We can do deep learning. They're running Linux. We have the ability to do segmentation, object detection. Everything you've heard about, you can now do on your desktop for just a couple $100. And the software, of course, is what drives it. Not just the deep learning frameworks, but also the simulation and the cloud compute that makes it possible to collect data on the edge and then train in the cloud. This is an example of what a virtual race looks like today, and this is just one of our races. It's we call this the pandemic edition. So this will show you how we race head to head, and the two cars will actually be starting at the same time, both running autonomously, and doing multiple laps. They run into each other. It's like Mario Kart, but all in autonomy. Now you may have heard that there is a full-scale, there's probably several full-scale autonomous car racing leagues, and the one that's perhaps most famous is RoboRace. And so there is absolutely an autonomous car racing league. However, because these cars are full-size and so expensive, they're like $1 million each, they've been extremely reluctant to do head-to-head racing, like a real race. When they do head-to-head racing, they actually have a driver in the car, and when they don't do head-to-head racing, when they're doing just time trials, they'll do it autonomous, but it's not been working out all that well. And you may have seen just this very week that there was a time trial in the UK, and this is the second race of the event, and it starts and goes straight into a wall. Now, my sympathies. We do that all the time. It happens. Maybe somebody just forgot to start the model, glitches, etc. The difference is that that's $1 million car that just ran into a wall, as opposed to a $100 car that just bounced off a bit of foam. So if you're going to make mistakes, it's a lot easier to make mistakes when they are cheap and safe and done in an indoor track where nobody gets hurt. So just to show you, just to prove that we too crash a lot, I wanted to show this video, which is what we call the demolition derby. At the end of the race, we make all the cars run together, and it is a complete fiasco. And you can see that cars not only hit each other, they hit spectators. Here's a kid who's amazingly manages to not fall down, but it's complete chaos, and it is super fun, and nobody cares who wins. And as you can see, we have participants who range from 8 years old to 80 years old. Some of them are middle school students, and some of them work for Google. And it's really, there's something for everybody, and the crashing in our case is a lot of fun rather than an embarrassment on YouTube. So I mentioned that this is just us starting as a community, but we've inspired some of the biggest companies in the world to do the same thing. Now, Amazon, NVIDIA, and Intel all have DIY Robocar projects. The Amazon one is an actual product called Deep Racer that you can buy, and they have it integrated with their SageMaker environment. This is training and simulation environment. NVIDIA has, is in there with their Jetson Nano, has come out with 2 cars. One JetBot, which is designed to be slowly kind of looking through, driving through a simulated village, or kind of a small scale village, doing stop signs and pedestrians. And then they have a racing one as well called Jet Racer. And Intel just released one called OpenBot, which uses your smartphone as the brain and camera. And again, is already it's all trained. The software is ready to be loaded on your smartphone, and all of them recognize that this is a great way to learn AI and to experiment with edge compute, doing AI in the real world on low-cost devices, that aren't necessarily connected to the internet all the time, but do have the ability to go to the cloud for training. Now, if you want to get started, you don't even have to build your own one. There's a number of DIY Robocars out there that you can just buy that are a great way to explore some of these techniques here. The 3 that I highlighted and like, there's a really cute one called the Zoomy, which uses a Raspberry Pi Zero, uses the Jupyter framework and Python and computer vision and deep learning. And that's, again, a little bit like that JetBot, where it navigates a little town, and like a Lego scale town, and great way to teach, very fun for kids. There's another one called the TinkerGen Mark, which does the same thing, a little bit larger. A slightly more powerful processor. Again, comes with pre-trained networks and computer vision, etc. And then if you like the Jetson, JetBot or the Donkey Car, you can actually buy those pre-made from a company called Waveshare, and you can just Google that, and you can find the link. But so that's basically the way you can get started. You can do it in your backyard. You can do it in your basement. Tape on the ground, chalk, anything. The point is that autonomous cars are now within reach, and with that comes all of the most advanced computer vision, deep learning, training techniques that you read about. But now you don't just have to read about anymore. You can do it yourself. AI is as you know, the future, but AI in the real world is really the future. And everything works in simulation. Nothing works in the real world the first time. This is a great time to really stress test your understanding of AI, of model creation, of training techniques with real world data, and have a lot of fun while you're doing it. So with that, thank you very much. And I think we're later going to have a Ask Me Anything session where we can explore all the questions you may have. And here's some links you can use to get started. Thanks again.